The Wiener filter is an optimal filter for doing image restoration in the presence of additive Gaussian noise. Instead of using this formula then for direct inverse filtering with its problems, with its blow-up problems because of H on the bottom line, we can develop the Wiener filter, which has an equation looking like this here, which doesn't blow up but requires the image power spectrum. We need to know what the image power spectrum and the noise power spectrum. We need to know what the noise is at all frequencies. That usually we don't know. So we use an approximation here for the Wiener filter, which usually works quite well. Instead of the noise power spectrum, we have this adjustable parameter K, which is really the inverse of the signal to noise ratio. So I want you to do activity 8.2 from the book, and we'll do part of activity 8.3 and then you'll finish it. So if we go to image J and open up chapter 8 activities, which you've downloaded the zip file and unzipped it, I went to open blurred.tiff and open pillbox.tiff, and we'll make duplicates of each. Duplicate of that one and a duplicate of this one. And we'll try straight deconvolution first. Of course, this is happening in the frequency domain. We'll go to Process, FFT, FD Math, and we'll put in the image that we want to restore is blurred1.tiff. We want to do a deconvolution and pillbox 1 and check this here, do the inverse transform, and we'll try it, and it's hopeless. I mean, it just doesn't work because of that problem that we know about, and also because this point spread function here isn't good, and we haven't allowed for any noise. You could try doing it with, let me show you in here, with one of the other point spread functions, either a scaled pillbox function, that's the brick wall function, or a Gaussian, and see if it works at all. So it hasn't worked there. Let's then try the Wiener filter. I mean, we could look at this image here and go to plugins chapter 5 and get the signal to noise ratio off it. Remember how that is. You make a region of interest of a boring region where nothing's happening, and then you use that plugin. But I'll not do that. You can try doing that and get the signal to noise ratio and invert it to get our capital K. But I'll go straight ahead and use plugin chapter 8 Wiener filter. We're using the blurred image here and the pillbox there, floating point output, and let's use double precision, and let's use, this is K, they've called it gamma, 1 over the signal to noise ratio. Let's keep it on the default 0.01, which means the signal to noise ratio in this image is 100. And we'll click on it, and we get something from which we can actually read the registration plate now, but it's not optimal. It's got a lot of ringing due to the hard edges in the point spread function. So you could try different point spread functions, different sizes, and use a Gaussian, and you can make up your own, or you can scale mine up or down, but make sure you end up with a 256 by 256 image for the point spread function, and use different values of K and see whether you can improve on this. And also look at some of the other images that are mentioned in activity 8.3 and try to restore them, try to de-blur them.